Tonight, we're going to explore one of the most fundamental yet overlooked features of the universe. Everything spins. Your planet spins on its axis once every 24 hours. The Moon spins as it orbits Earth. Earth orbits the Sun, which itself is spinning. The Sun orbits the center of the Milky Way galaxy, which is also spinning. And the Milky Way is part of a local group of galaxies that all have their own rotations. From the smallest asteroids to the largest galaxy clusters, rotation is everywhere. But here's what's going to challenge everything you think you understand. This isn't random. There's a reason everything spins, and that reason reaches back to the very beginning of the universe itself. By the end of tonight, you're going to understand why rotation is written into the fabric of reality and why a universe without spin would be fundamentally impossible. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about throwing a ball. When you toss a ball through the air, it follows a curved path, an arc determined by the force of the throw and Earth's gravity pulling it down. Simple mechanics that Newton described over 300 years ago. But here's something you might not have noticed. That ball is always spinning. Always. You can't throw a ball without giving it at least some rotation. Your fingers don't release it perfectly symmetrically. Air currents push on different parts of the surface unequally. Perfect symmetry doesn't exist in practice. There are always tiny imperfections, tiny asymmetries, tiny forces acting slightly off-center. And when forces act off-center, they create rotation. This same principle applies throughout the universe, but on scales vastly larger and more dramatic. Let's start with Earth's rotation because it's familiar and we experience it every day. Earth spins on its axis once every 23 hours and 56 minutes. Not exactly 24 hours, but close enough for everyday purposes. This rotation gives us day and night as different parts of the planet face toward and away from the Sun. At the equator, you're moving at about 1,040 miles per hour due to this rotation. That's faster than the speed of sound. You don't feel this motion because everything around you, the air, the ground, the buildings, is moving at the same speed, but you can see the effects. The Coriolis effect causes hurricanes to spiral, makes wind patterns curve, and would cause a ball dropped from a tall tower to land slightly east of where you might expect. Why does Earth spin? The answer takes us back 4.5 billion years to the formation of the solar system. The solar system formed from a cloud of gas and dust called the solar nebula. This nebula was huge, spanning several light years across. It consisted mostly of hydrogen and helium left over from the Big Bang, mixed with heavier elements created in previous generations of stars that had lived, died, and scattered their remains. This nebula wasn't sitting still. It was moving. Different parts of it had different velocities. Some regions were moving slightly faster, some slightly slower. Some were drifting one direction, some another. This is crucially important. In all the vast expanse of interstellar space, you will never find a cloud of gas that is perfectly at rest, with all its parts moving in exactly the same direction at exactly the same speed. It doesn't happen. Random turbulence from nearby stars, shock waves from distant supernova explosions, gravitational tugs from passing molecular clouds. All of these create motion and create differences in motion. And where there are differences in motion, there is angular momentum. Angular momentum is one of the most important concepts in physics. It's the rotational equivalent of regular momentum. Just as an object moving in a straight line has momentum equal to its mass times its velocity, a rotating object has angular momentum related to how fast it's spinning and how its mass is distributed. The critical property of angular momentum is that it's conserved. In a closed system with no external torques, the total angular momentum stays constant. This conservation law is as fundamental as the conservation of energy or the conservation of momentum. It's one of the bedrock principles of physics, derived from the symmetry of physical laws with respect to rotation. When the solar nebula began to collapse under its own gravity, perhaps triggered by the shock wave from a nearby supernova, it started pulling itself together. Gas and dust fell inward toward the center where gravity was strongest. As it collapsed, something happened that's both intuitive and remarkable. It started spinning faster. You've seen this if you've ever watched a figure skater. When a skater starts a spin with arms extended and then pulls their arms in close to their body, they spin faster, much faster. This isn't because they're pushing off with their feet or doing anything to add energy. It's pure conservation of angular momentum. As the skater's mass moves closer to the axis of rotation, the rotation rate must increase to keep the total angular momentum constant. The same thing happened with the solar nebula. As it collapsed from a diffuse cloud several light-years across, down to a dense region just a few billion miles across, all that angular momentum got concentrated. The nebula spun faster and faster. But something else happened too. The nebula didn't collapse into a sphere. It flattened into a disk. This is a crucial point that explains so much about the structure of the solar system and planetary systems around other stars. Why a disk? Because of the interplay between gravity, rotation, and collisions. Gravity pulls everything toward the center equally in all directions. But rotation creates centrifugal effects that resist collapse perpendicular to the axis of rotation. Imagine the nebula rotating like a wheel. Material, trying to fall toward the center along the axis of rotation, through the poles, encounters no resistance from rotation. It falls straight in. But material trying to fall toward the center, perpendicular to the axis, through the equator, experiences rotational motion that prevents it from falling straight in. Instead, it settles into orbits around the center. At the same time, particles in the nebula are colliding with each other constantly. Gas molecules bouncing off each other, dust grains bumping together. These collisions average out random motions. A particle moving steeply up out of the plane collides with other particles and gets knocked back down. Another particle moving steeply down collides and gets knocked back up. Over millions of collisions, all the random up and down motion gets damped out. What remains is the organized circular motion around the center. The result is a flat disk of material all orbiting in roughly the same direction around a dense central condensation. This disk is called a protoplanetary disk. It's where planets form. At the center, where density and temperature are highest, hydrogen fusion eventually ignites, creating a star. That's your sun. In the disk around it, dust grains stick together, forming larger clumps. Those clumps attract more material gravitationally, growing into planetesimals, then protoplanets, then finally full planets. Earth formed from countless collisions between these smaller bodies. And every single collision imparted angular momentum. Imagine two planetesimals, each a few hundred miles across, on slightly different orbits. They collide, but not head-on. Almost never head-on. Space is three-dimensional, and orbits are complex. The collision happens at an angle, off-center. When one body hits another off-center, it starts the combined object rotating. It's like hitting a pool ball off-center with the cue. The ball doesn't just move in a straight line, it spins. Over millions of years, as Earth grew through countless such collisions, all those angular momentum contributions added up. The result was a planet spinning on its axis. The direction of that spin, the tilt of the axis, even the length of the day, all of these were determined by the details of those collisions. They're essentially random outcomes of a chaotic process. Earth's axis is tilted 23.5 degrees relative to its orbit around the Sun. That tilt gives us seasons. When the northern hemisphere is tilted toward the Sun, it's summer there and winter in the southern hemisphere. 6 months later, the situation reverses. But why 23.5 degrees specifically? Why not 30 degrees or 15 or 0? Because that's what resulted from the particular collisions that formed Earth. A different sequence of impacts would have given a different tilt. In fact, there's strong evidence that early in its history, Earth was hit by a Mars-sized object called Theia. This impact was so violent, it threw an enormous amount of material into orbit around Earth. That material eventually coalesced to form the Moon. The impact also likely changed Earth's rotation, possibly creating the current axial tilt, or at least modifying it significantly. So, Earth spins because of the angular momentum inherited from the solar nebula and modified by billions of years of collisions during its formation. But Earth's spin is slowing down. Very gradually, but measurably. The day is getting longer by about 1.7 milliseconds per century. This might not sound like much, but over hundreds of millions of years it adds up. 400 million years ago, during the Devonian period, when fish were first crawling onto land, a day was about 21.5 hours long. There were about 410 days in a year, instead of 365. What's causing this slowdown? The Moon. Specifically, tidal friction between Earth and the Moon. The Moon's gravity pulls on Earth, creating tides in the oceans. The side of Earth facing the Moon experiences a stronger gravitational pull than the far side, so water bulges toward the Moon and also on the opposite side of Earth. As Earth rotates, these tidal bulges try to stay aligned with the Moon. But friction with the ocean floor and the viscosity of the water itself mean the bulges don't stay perfectly aligned. Earth's rotation drags the tidal bulge slightly ahead of the Moon. The Moon's gravity pulls back on this bulge, creating a torque that slows Earth's rotation. At the same time, by Newton's third law, Earth's gravity pulls on the Moon, and because the tidal bulge is ahead of the Moon's position, this pull has a component in the direction of the Moon's orbit. This speeds up the Moon, giving it more orbital energy and causing it to slowly spiral outward away from Earth. So Earth's rotation is slowing down and the Moon is moving away. Both effects are consequences of conservation of angular momentum. The angular momentum lost by Earth's rotation is gained by the Moon's orbit. The total angular momentum of the Earth-Moon system stays constant, but it's being redistributed. Eventually, in billions of years, Earth and Moon will reach a state called tidal locking, where Earth rotates at the same rate the Moon orbits. At that point, the same side of Earth will always face the Moon, just as the same side of the Moon always faces Earth today. The Moon is already tidally locked to Earth. It rotates once per orbit, which is why we always see the same face. This happened because Earth's gravity created tides in the Moon's rock. Yes, rock tides. The moon is solid, but over millions of years, even solid rock can flow slightly in response to strong gravitational forces. These rock tides created friction that slowed the moon's rotation until it matched its orbital period. Tidal locking is common throughout the solar system. Most of the moons of Jupiter and Saturn are tidally locked to their planets. Pluto and its largest moon Charon are mutually tidally locked. They always show the same face to each other. Mercury is in a 3-to-2 spin-orbit resonance with the Sun. It rotates 3 times for every 2 orbits, a stable configuration created by tidal forces and Mercury's slightly elliptical orbit. Let's zoom out now and look at the Sun. The Sun is also spinning. It rotates on its axis once every 25 days at its equator. But here's something weird. The Sun doesn't rotate as a solid body. It's a ball of plasma, ionized gas, and different parts rotate at different speeds. At the equator, the rotation period is about 25 days. At mid-latitudes, it's about 27 days. Near the poles, it takes over 30 days. This differential rotation is possible because the Sun isn't solid. There's no rigid surface, forcing everything to rotate together. Instead, the plasma flows and circulates, driven by complex fluid dynamics and the Sun's magnetic field. This differential rotation is actually crucial for generating the Sun's magnetic field through a process called the solar dynamo. Moving plasma carries electrical currents, and electrical currents generate magnetic fields. The combination of rotation and convection in the Sun's interior twists and amplifies magnetic field lines, creating the complex magnetic structures we observe. These magnetic fields manifest as sunspots, solar flares, coronal mass ejections, and the 11-year solar cycle. But why is the Sun spinning at all? Same reason Earth is spinning. It formed from the rotating solar nebula. As the center of the nebula collapsed to form the Sun, it inherited the angular momentum of the material that fell into it. You might think the Sun should be spinning much faster than it actually is. If you took all the angular momentum of the original nebula and concentrated it into a body the size of the Sun should be rotating once every few hours, not once every 25 days. So, where did the angular momentum go? Into the planets and the solar wind. As the solar system formed, most of the mass ended up in the Sun, about 99.86% of the total. But most of the angular momentum ended up in the planets, especially Jupiter. Jupiter alone contains about 60% of the solar system's angular momentum, even though it's less than 0.1% of the mass. This happened because angular momentum depends not just on how fast something is moving, but also on how far it is from the axis of rotation. An object far from the center can have more angular momentum than a faster moving object close to the center. Jupiter is far from the Sun and moving in a large orbit, so even though it's moving much slower than the Sun's surface rotates, it carries far more angular momentum. Additionally, the young Sun lost angular momentum through its solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun in all directions. This wind carries away both mass and angular momentum. The Sun's magnetic field extends far out into space, and the solar wind particles are constrained to move along magnetic field lines. As they move outward, they carry angular momentum with them, slowing the Sun's rotation over time. This process, called magnetic braking, has slowed the Sun considerably since it first formed 4.5 billion years ago. Young stars rotate much faster than old stars. Some young stars rotate so fast they complete one rotation in just a few hours. As they age and lose angular momentum to their stellar winds and potentially to planetary systems, their rotation slows. Now, let's zoom out further. The Sun isn't stationary in space. It's orbiting the center of the Milky Way galaxy. The Sun is about 26,000 light-years from the galactic center, and it takes about 225 million years to complete one orbit. This is called a galactic year or a cosmic year. Since the Sun formed 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. When dinosaurs walked on Earth, the Sun was on the opposite side of the galaxy. When the first complex life appeared in Earth's oceans about 600 million years ago, the Sun was about 3 galactic years younger. And the Sun isn't alone in this orbit. All the stars in the solar neighborhood, the nearby stars you see in the night sky, are moving in similar orbits around the galactic center. We're all part of the rotating disk of the Milky Way. The Milky Way itself is spinning. It's a spiral galaxy, and that spiral structure is intimately connected to the galaxy's rotation. The entire disk of the galaxy rotates around the galactic center, but not like a solid wheel. Different parts rotate at different speeds in a complex pattern determined by the distribution of mass in the galaxy. Near the center, where there's a lot of mass in a small volume, stars orbit quickly. Farther out, orbital speeds are slower, but don't drop off as quickly as you might expect based on the visible mass. This is one of the key pieces of evidence for dark matter. Based on the stars we can see, orbital speeds should drop significantly as you go farther from the center, following the same pattern we see in the solar system, where outer planets move slower than inner planets. But they don't. Orbital speeds stay roughly constant, even far from the galactic center. This implies there's additional mass we can't see, providing the extra gravity needed to keep stars moving as fast as they are. This is dark matter, and it appears to make up about 85% of the matter in the galaxy. The spiral arms you see in images of the Milky Way and other spiral galaxies aren't permanent structures. They're density waves, regions where stars and gas are temporarily more crowded together. Think of a traffic jam on a highway. Cars enter the jam, slow down, then exit the other side. The jam itself, the region of crowded cars, can stay in one place, even though individual cars are moving through it. Spiral arms work similarly. They're regions where the density of stars is higher, created by the gravitational interactions between stars and the rotation of the galaxy. Stars move into a spiral arm, spend some time there, then move out the other side. But the arm itself persists as a structure rotating around the galactic center. Why does the Milky Way have spiral arms? Why is it rotating at all? Same answer as before. Angular momentum from the original cloud of gas that collapsed to form the galaxy. Galaxies formed in the early universe from irregularities in the distribution of matter. Some regions were slightly denser than average. Gravity pulled matter toward these dense regions. As matter fell inward, it brought its angular momentum with it. The proto-galaxy started to spin faster as it contracted, just like the solar nebula did. And just like the solar nebula, the collapsing cloud flattened into a disk due to rotation and collisions. Gas clouds within the galaxy collided, averaged out random motions, and settled into the plane of the disk. Stars formed from this gas, and they inherited the rotation of the disk. The result is what we see today, a flattened disk of stars orbiting the galactic center with spiral structure created by density waves. But not all galaxies are spirals. Many galaxies, especially the largest ones, are elliptical. Elliptical galaxies don't have the flattened disk structure of spirals. Instead, they're roughly spherical or football-shaped, with stars moving in random orbits rather than all moving in the same direction in a plane. How did this happen? Galaxy mergers. When two spiral galaxies collide and merge, the organized rotation of both galaxies gets disrupted. Stars are scattered into new orbits, some moving one direction, some another. The net rotation of the combined system might be close to zero, or at least not organized into a single rotating disk. The result is an elliptical galaxy, where individual stars are orbiting the galactic center, but not in any organized pattern. The galaxy as a whole doesn't have a strong net rotation. This tells us something important. Rotation requires organization. It requires that most of the mass is moving in roughly the same direction. When that organization is destroyed through a violent event like a galaxy merger, rotation can be lost even though angular momentum is conserved. The angular momentum gets distributed among stars moving in many different directions, so there's no net rotation of the galaxy as a whole. But even elliptical galaxies formed from rotating clouds initially. They've just had their rotation disrupted by mergers. And many elliptical galaxies still show some rotation if you look carefully enough. It's just not as organized as in a spiral galaxy. Let's zoom out even further to galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain dozens to thousands of galaxies held together by their mutual gravity. And many galaxy clusters show overall rotation. The galaxies within the cluster are all orbiting the cluster's center of mass. This rotation is slow, taking billions of years for a single orbit. But it's there, and it's measurable. Galaxy clusters rotate because they formed from rotating regions of the early universe. Even on these enormous scales, spanning tens of millions of light-years, angular momentum is conserved. The rotating motion of the original matter is still present, just distributed among hundreds or thousands of galaxies. At even larger scales, we see structure in the universe that hints at rotation. The cosmic web, the large-scale structure of the universe, consists of filaments of galaxies connecting dense nodes with vast voids in between. Some of these filaments show evidence of rotation. Galaxies along a filament might all be moving with a slight rotational component around the filament's axis. This is controversial and difficult to measure because the rotations are so slow and the distances so vast that small errors can hide or mimic rotation. But if it's real, it would be rotation on scales of hundreds of millions of light-years, the largest rotating structures in the universe. Now, let's come back down to smaller scales and talk about something that might seem unrelated but isn't. Black holes. Black holes rotate. Almost certainly, all black holes rotate because they form from rotating matter. When a massive star runs out of fuel, its core collapses in a supernova explosion. If the core is massive enough, more than about 3 times the mass of the Sun, it collapses into a black hole. That core was rotating before the collapse. Stars rotate, as we've discussed. When the core collapses, conservation of angular momentum means the rotation speeds up dramatically. just like the figure skater pulling in their arms. As the core shrinks from thousands of miles across to a point, its rotation accelerates. The result is a black hole that's spinning, sometimes spinning at nearly the maximum rate allowed by the laws of physics. The rotation of a black hole has observable consequences. A rotating black hole drags space-time around with it in an effect called frame dragging. Anything near the black hole, even light itself, gets caught up in this rotating space-time and dragged along. There's a region around a rotating black hole called the ergosphere, where this frame dragging is so strong that nothing can remain stationary. Everything must move in the direction of the black hole's rotation, even if it's trying to move the opposite way. This isn't because of a force pulling things along. It's because space-time itself is rotating. The distinction between moving and not moving has changed. Rotating black holes are described by a solution to Einstein's equations called the Kerr metric, discovered by Roy Kerr in 1963. The Kerr solution shows that a rotating black hole has a more complex structure than a non-rotating one. It has two event horizons, an inner and an outer, and a ring-shaped singularity instead of a point singularity. The rotation also makes it theoretically possible, though probably not practically feasible, to extract energy from a black hole through a process called the Penrose process. You could send an object into the ergosphere, have it split into two pieces, and arrange things so that one piece falls into the black hole while the other escapes. If done correctly, the escaping piece can have more energy than the original object, with the difference coming from the black hole's rotational energy. The black hole slows down slightly, and you've extracted energy. This probably doesn't happen naturally, but it's a consequence of the mathematical description of rotating black holes. Supermassive black holes at the centers of galaxies also rotate. The supermassive black hole at the center of the Milky Way, called Sagittarius A star, is rotating. We can infer this from observations of stars and gas orbiting very close to it. Many supermassive black holes are surrounded by accretion disks, swirling disks of gas and dust falling toward the black hole. These disks are rotating, and they feed angular momentum into the black hole as material falls in. The black hole's rotation affects how the accretion disk behaves. The disk's inner edge is determined by the black hole's rotation. For a fast-spinning black hole, the disk can extend closer to the event horizon. For a slowly spinning black hole, the disk is pushed farther out. This affects the temperature of the disk, which affects how much radiation it emits, which is something we can observe with telescopes. Some supermassive black holes launch enormous jets of particles and radiation from their poles, extending for millions of light-years into intergalactic space. These jets are thought to be powered by the black hole's rotation. The details are complex and still not fully understood, but the basic idea is that magnetic fields, threading the accretion disk and the rotating spacetime around the black hole, work together to accelerate particles to nearly the speed of light and funnel them out along the rotation axis. The rotation of the black hole provides the energy for these jets. So as the jets are powered, the black hole's rotation slows down slightly. Let's think about rotation on the smallest scales now. Atoms don't rotate in the classical sense, but fundamental particles have a property called spin. Despite the name, this isn't actual rotation. An electron isn't a tiny spinning ball. The electron appears to be a point particle with no size, so there's nothing to spin. But electrons do have angular momentum, and this angular momentum is quantized, meaning it comes in discrete units. an electron has a spin of 1/2 in units where the quantum of angular momentum is 1. This spin is intrinsic to the electron. It's not caused by anything, it's just a property the electron has, like its mass or charge. The spin of elementary particles plays a crucial role in the structure of matter. The Pauli exclusion principle states that no two fermions, particles with half-integer spin like electrons, can occupy the same quantum state. This is why atoms have shells of electrons rather than all electrons falling into the lowest energy state. It's why matter has the structure and properties it does. Without spin and the exclusion principle, chemistry would be completely different, and matter as we know it wouldn't exist. Photons, particles of light, also have spin. Photons have a spin of 1, making them bosons. The spin of a photon corresponds to the polarization of light. Light can be circularly polarized, spinning like a corkscrew as it travels. Right-handed circular polarization corresponds to one spin direction, left-handed to the opposite spin direction. When you observe rotating objects in space using polarized light, you can learn about their rotation from how the light's polarization changes. So even at the quantum level, the concept of spin and rotation is fundamental. Let's think about why rotation is so ubiquitous. Why does everything spin? The fundamental answer comes down to symmetry and conservation laws. In physics, conservation laws arise from symmetries. The conservation of energy arises from time translation symmetry, the fact that the laws of physics don't change with time. The conservation of momentum arises from space translation symmetry, the fact that the laws of physics are the same everywhere in space. And the conservation of angular momentum arises from rotational symmetry, the fact that the laws of physics don't depend on which direction you choose to call up or down, north or south. Because the universe has rotational symmetry, angular momentum is conserved. And because angular momentum is conserved, rotation can never disappear. Once something is rotating, it will keep rotating unless something else applies a torque to it. But applying a torque requires angular momentum to come from somewhere or go somewhere. You can transfer angular momentum between objects, but you can't destroy it. This is why rotation is so common. The early universe was filled with tiny irregularities, quantum fluctuations that grew into the structures we see today. These irregularities meant different regions of space had slightly different velocities. Differences in velocity mean angular momentum. As these regions collapsed under gravity to form stars, galaxies, and galaxy clusters, that angular momentum got concentrated. Rotation increased. And once that rotation was established, it persisted because angular momentum is conserved. So, in a very real sense, the rotation we see everywhere in the universe today, from planets to galaxies to black holes, is the echo of tiny differences in motion in the very early universe. It's the accumulation and concentration of angular momentum that was present from the beginning. But there's a deeper question. Could the universe itself be rotating? This is a speculative and controversial idea. Einstein's equations allow for rotating universe solutions. The most famous is the Gödel universe, proposed by mathematician Kurt Gödel in 1949. In a Gödel universe, space-time itself rotates. There's no fixed frame of reference. Everything is rotating relative to everything else in a consistent way. Gödel's solution also allows for closed time-like curves. paths through spacetime that loop back on themselves. You could theoretically travel into your own past, creating paradoxes. For this and other reasons, the Gödel universe is not thought to describe our actual universe. But it shows that Einstein's equations don't forbid a rotating universe. So could our universe be rotating? Current observations suggest it isn't, or if it is, the rotation is extremely slow. We can look for evidence of rotation by checking if the universe looks the same in all directions. If the universe were rotating, there would be a preferred axis, and properties of the universe, like the expansion rate or the temperature of the cosmic microwave background, would be different in different directions. Detailed measurements of the cosmic microwave background show that it's remarkably uniform in all directions. There are tiny variations, but these variations are consistent with random quantum fluctuations, not with a large-scale rotation. So to very high precision, the universe doesn't appear to be rotating. But we can only observe the part of the universe within our observable horizon, about 93 billion light-years across. The entire universe could be much, much larger. If the universe is rotating, but the rotation axis is very far away, much farther than we can see, then we wouldn't detect it. We'd be like an ant on a slowly rotating disk, too small to measure the curve. So it remains possible, though not supported by current evidence, that the universe on scales larger than we can observe is rotating. If it is, that rotation would have been present from the very beginning, from the Big Bang itself. There's also the question of whether the Big Bang itself was rotating. This leads to deep questions about the origin of angular momentum in the universe. If the universe started from a perfectly symmetric initial state, where would rotation come from? One possibility is that the initial state wasn't perfectly symmetric. Quantum mechanics tells us that perfect symmetry is impossible. There are always quantum fluctuations, random variations at the smallest scales. These fluctuations could have given the early universe tiny amounts of angular momentum in different regions. As these regions expanded and evolved, that angular momentum got amplified and distributed into the structures we see today. Another possibility involves quantum mechanics at a deeper level. In quantum field theory, even empty space isn't truly empty. It's filled with quantum fields that fluctuate randomly. These fluctuations could create particle-antiparticle pairs that briefly exist before annihilating. If these fluctuations happened in the early universe, when spacetime itself was fluctuating wildly, they could have imparted angular momentum to different regions. But these are speculative ideas at the frontier of theoretical physics. We don't have direct evidence for exactly how angular momentum originated in the universe. What we do know is that it exists, it's conserved, and it's everywhere. Let's come back to something more concrete and think about what would happen if rotation suddenly disappeared. Imagine if Earth stopped spinning but continued orbiting the Sun. First, everything not firmly attached to the ground would keep moving. Buildings, cars, the oceans, the atmosphere, all of it is moving at about 1,040 miles per hour at the equator due to Earth's rotation. If Earth stopped and you didn't, you'd fly eastward at 1,040 miles per hour. The results would be catastrophic, beyond comprehension. The oceans would surge eastward in a colossal tsunami that would submerge entire continents. The atmosphere would continue moving, creating winds far stronger than any hurricane. Eventually, after the chaos settled, you'd be left with a very different planet. One side would face the sun continuously. That side would heat up to extreme temperatures as it baked under constant sunlight. The other side would be in eternal darkness, cooling to frigid temperatures. The boundary between day and night would be the only habitable zone, a narrow ring around the planet where temperatures were moderate. Weather patterns would be completely different, with heat from the day side trying to flow to the night side, creating permanent storm systems along the terminator. Earth's magnetic field would probably disappear. The magnetic field is generated by electric currents in Earth's liquid iron core, and these currents are driven by convection, combined with rotation. Without rotation, the dynamo would shut down and the magnetic field would decay. Without a magnetic field, the solar wind would strip away the atmosphere over millions of years. So stopping Earth's rotation would make it uninhabitable in multiple ways. What if the sun stopped rotating? The sun's magnetic field, as mentioned earlier, is generated by a dynamo process that requires rotation and convection. Without rotation, there would be no dynamo. The magnetic field would disappear. Without a magnetic field, there would be no sunspots, no solar flares, no coronal mass ejections. The sun would be magnetically quiet. This might actually be beneficial for Earth, as solar storms can damage satellites and power grids. But it would change the sun's structure in subtle ways that are hard to predict. What if galaxies stopped rotating? This is harder to imagine because galaxies are held together by gravity, and their rotation is what keeps them from collapsing. If you could somehow remove all rotation from a galaxy, every star would fall directly toward the center under gravity. The galaxy would collapse into a dense ball, probably forming a supermassive black hole at the center. The fact that galaxies are stable, maintaining their structure over billions of years, is directly because of rotation. Rotation provides the centrifugal effect that balances gravity. This is true at all scales. Planetary systems are stable because planets orbit rather than falling into the sun. Galaxies are stable because stars orbit rather than falling into the galactic center. Even atoms are stable in a certain sense because electrons have angular momentum that keeps them from spiraling into the nucleus. Though this is quantum mechanical, and the classical picture of orbiting electrons isn't quite right. But the principle holds. Rotation, or more precisely, angular momentum, is essential for the stability and structure of matter at all scales. Let's think about some unusual examples of rotation in the universe. Pulsars are rotating neutron stars. When a massive star explodes in a supernova, it can leave behind a neutron star, an object about 10 miles across but containing more mass than the Sun. The density is incredible, comparable to the density of an atomic nucleus. If you could take a teaspoon of neutron star material and bring it to Earth, it would weigh about 1 billion tons. Neutron stars form from the collapsed cores of massive stars, and like all collapsing rotating objects, they spin faster as they shrink. Some neutron stars rotate incredibly fast. The fastest known pulsar rotates 716 times per second. 716 revolutions per second for an object 10 miles across. The surface is moving at a significant fraction of the speed of light. These rapidly rotating neutron stars emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams. If one of the beams happens to point toward Earth, we see a pulse of radiation each time it sweeps past. That's why they're called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She noticed regular radio pulses from space, arriving with astonishing precision. The pulses were so regular, with a period of 1.337 seconds, that the team half-jokingly considered whether they might be signals from an alien civilization. They even nicknamed the source LGM-1 for Little Green Men. But soon more pulsars were discovered, and it became clear these were natural objects. They were rotating neutron stars. The regularity of pulsar pulses is extraordinary. The best pulsars keep time more accurately than atomic clocks. Astronomers have used pulsars as natural clocks to test relativity, detect gravitational waves, and probe the structure of spacetime. The slowest known pulsars rotate about once every 10 seconds. The fastest, as mentioned, rotate hundreds of times per second. This enormous range is due to different ages and histories. Young pulsars, born in supernova explosions, are rotating fast. Over time, they slow down as their rotation energy is carried away by magnetic fields and radiation. Old pulsars are rotating slowly, but some old pulsars get spun back up. If a neutron star is in a binary system with a normal star, material from the companion can fall onto the neutron star. This material carries angular momentum, and as it spirals onto the neutron star, it spins the neutron star up. These recycled pulsars can end up rotating very fast, even faster than young pulsars. This process explains the millisecond pulsars, pulsars rotating hundreds of times per second. They're old neutron stars that have been spun up by accreting material from companions. Another unusual rotating object is a white dwarf in a binary system called a cataclysmic variable. White dwarfs are the remnants of stars like the Sun after they've exhausted their nuclear fuel. They're about the size of Earth, but contain about the mass of the Sun. If a white dwarf has a close companion star, it can pull material from the companion. This material forms an accretion disk around the white dwarf, a rotating disk of gas spiraling inward. As the gas spirals in, it heats up from friction and releases enormous amounts of energy, making the system bright in X-rays and ultraviolet light. The rotation of the disk, the rotation of the white dwarf itself, and the orbital motion of the two stars all contribute to complex dynamics. Sometimes the material accumulates on the white dwarf's surface until it reaches a critical density and temperature. Then it undergoes a sudden burst of nuclear fusion, a nova, briefly making the system thousands of times brighter. These events are triggered by the accumulation of rotating material from the accretion disk. At a completely different scale, we have rotating stars in binary systems. Many stars are not alone, but part of binary or multiple star systems. Two stars orbiting each other around a common center of mass. This orbital motion is rotation. The two stars are rotating around their shared center of mass just like planets orbit the Sun. Some binary stars are very close together, orbiting in hours or days. These close binaries can interact in fascinating ways. If one star expands as it evolves, it can fill its Roche lobe, the region around it where its gravity dominates. Material from the expanding star can overflow this lobe and fall onto the companion. This creates mass transfer, and the transferred material brings angular momentum, which can change the orbital period and the spins of both stars. Some binary stars are so close they actually touch, with material streaming between them. These are called contact binaries. They're essentially two stars sharing a common envelope of gas. The rotation of the system is crucial for their structure and evolution. In our solar system, we have rotating asteroids and comets. These objects spin as they orbit the Sun, and some spin very rapidly. The fastest rotating asteroids complete one rotation in just a few minutes. If they rotated much faster, they'd tear themselves apart. The centrifugal force from rotation would overcome the gravity and structural strength, holding them together, and pieces would fly off. This actually does happen sometimes. Some asteroids have been observed to break apart due to rotation. They might get spun up by the Yorp effect, a subtle torque created by the way they absorb and re-emit sunlight. Sunlight carries momentum, and if an asteroid has an irregular shape, the absorption and emission of sunlight can create a net torque that slowly spins it up over thousands of years. Eventually, if the spin gets too fast, the asteroid flies apart. We've also discovered that some asteroids are actually binary systems, two asteroids orbiting each other. The rotation of this system can be studied by observing how the brightness changes as the two asteroids eclipse each other. Comets also rotate as they orbit the Sun, and this rotation affects how gas and dust are ejected from their surfaces as they warm up near the Sun. The jets of gas and dust coming off a comet create a torque that can change the comet's rotation over time. The Rosetta spacecraft observed comet 67P Churyumov-Gerasimenko and found it rotating once every 12 hours. The rotation was irregular and changing because of the jets of gas being released as the comet warmed up. Let's think about rotation in the context of the universe's expansion. The universe is expanding, with galaxies moving away from each other as space itself expands. Does this expansion affect rotation? Not on small scales. Galaxy clusters that are gravitationally bound aren't expanding with the universe. They're held together by gravity. Similarly, galaxies, star systems, planets, all of these are not expanding because they're gravitationally bound. But on the largest scales, where structures aren't gravitationally bound, the expansion does affect things. The cosmic web, the filaments and voids that make up the large-scale structure of the universe, is expanding with the universe. If these filaments are rotating, which is still debated, then the expansion might affect that rotation in complex ways. As space expands, distances increase and velocities change. Angular momentum should still be conserved, but the distribution of that angular momentum changes as the universe expands. This is a subtle and technical topic that requires general relativity to properly describe. In an expanding universe, you can't define angular momentum the same way you do in flat, non-expanding space. The concept becomes ambiguous over large distances because there's no global reference frame. But locally, within regions that aren't expanding significantly, angular momentum conservation still holds. Let's talk about one more fascinating aspect of rotation: the frame dragging effect, predicted by general relativity. We mentioned this in the context of black holes, but it also occurs around any rotating massive object, including Earth. Einstein's theory predicts that a rotating body drags spacetime around with it, near Earth. This effect is incredibly tiny, but it's measurable. In 2004, NASA launched Gravity Probe B, a satellite designed to detect frame dragging around Earth. The satellite carried 4 gyroscopes, the most perfect spheres ever made, each one polished to within 40 atoms of perfect sphericity. The gyroscopes were set spinning and pointed at a distant star. Over the course of a year, the direction the gyroscopes pointed changed very slightly due to frame dragging. Earth's rotation dragged space-time around with it, and this dragging twisted the direction of the gyroscopes. The measured effect was about 39 milliarcseconds per year, in excellent agreement with Einstein's prediction. This is an incredibly small angle. If you extended that angle across the entire Earth, it would correspond to a shift of less than the width of a human hair. But it was measured, confirming that rotating bodies really do drag space-time around with them. Frame dragging has implications for satellites and spacecraft. Near a rapidly rotating object, the dragging of space-time can affect orbits in measurable ways. For GPS satellites orbiting Earth, frame dragging is a tiny correction that has to be accounted for to maintain the system's accuracy. For objects orbiting close to black holes, frame dragging is enormous and dominates the dynamics. So rotation affects the very fabric of space-time itself. It's not just objects moving through space. Rotation changes the geometry of space and time. Let's zoom all the way back out and think about the big picture. Why does everything in the universe spin? Because the universe has rotational symmetry, which gives us conservation of angular momentum. Because matter started with tiny differences in velocity, which became angular momentum as it collapsed under gravity. Because angular momentum can't disappear, only be transferred or redistributed. Because once something is rotating, it keeps rotating unless something else stops it. Rotation is as fundamental as motion itself. Linear motion, moving from one place to another, is governed by conservation of momentum. Rotational motion, spinning around an axis, is governed by conservation of angular momentum. Both are consequences of symmetries in the laws of physics. The universe doesn't care which direction is north or which point in space you call the origin. Because of these symmetries, momentum and angular momentum are conserved. And because they're conserved, motion and rotation persist. They're woven into the fabric of reality. Every spinning planet, every rotating star, every spiral galaxy, every black hole dragging space-time around with it, they're all manifestations of angular momentum. They're all echoes of the initial conditions of the universe, preserved and concentrated by gravity over billions of years. You can trace the rotation of Earth back through its formation from the solar nebula, back through the collapse of the nebula from an interstellar cloud, back through the formation of that cloud from gas enriched by previous generations of stars, back through the formation of those stars from the primordial gas of the early universe, back through the formation of structure from quantum fluctuations in the first moments after the Big Bang. At every step, angular momentum was there. At every step, it was conserved. At every step, it shaped how matter moved and organized itself. So when you watch the sun rise tomorrow morning, you're witnessing rotation, Earth spinning on its axis. When you see the moon in the sky, you're seeing rotation, the moon orbiting Earth, and Earth and moon orbiting their common center of mass. When you look at the Milky Way on a dark night, you're seeing rotation, the entire galaxy spinning majestically around its center. When you see images of distant spiral galaxies, you're seeing rotation, each one a rotating disk of hundreds of billions of stars. When you read about black holes detected by gravitational wave observatories, you're learning about rotation. Black holes spinning as they merge, releasing energy in the form of ripples in space-time itself. Rotation is everywhere because angular momentum is everywhere. And angular momentum is everywhere because it was present from the beginning and has been conserved ever since. The universe doesn't just contain rotation as one feature among many. Rotation is fundamental to its structure and evolution. Without rotation, galaxies wouldn't form the way they do. Stars wouldn't have planetary systems. Planets wouldn't have stable orbits. The universe would be a very different place, probably one where structures like galaxies and stars and planets couldn't exist at all. Everything would collapse under gravity, with nothing to provide the outward force needed for stability. So rotation isn't just common. It's necessary. It's what makes the universe the way it is. And it all comes down to symmetry and conservation laws, to the fundamental mathematical structure of physics, to the fact that the laws of nature don't depend on which direction you call up or down. That symmetry, that deep principle at the heart of physics, is why everything spins. It's why the universe is full of rotating objects at every scale. It's why, when you look up at the night sky, you're seeing a cosmos in motion, a universe that never stops spinning. Let's explore some more surprising examples of rotation that challenge our intuitions about how the universe works. Consider the rotation of planetary atmospheres. Earth's atmosphere rotates with the planet, but not uniformly. The lower atmosphere, the troposphere where we live and where weather happens, is mostly coupled to the surface through friction. It rotates at roughly the same speed as the ground below it. But higher up in the stratosphere and mesosphere, the coupling is weaker. Wind patterns can develop that move faster or slower than Earth's rotation. The jet streams, fast-flowing rivers of air high in the atmosphere, are created by the combination of Earth's rotation and temperature differences between the equator and poles. The Coriolis effect, a consequence of rotation, deflects moving air masses and creates the characteristic spiral patterns of storms and weather systems. Hurricanes and typhoons rotate because of Earth's rotation. In the northern hemisphere, they spin counterclockwise. In the southern hemisphere, they spin clockwise. This isn't because water drains differently in different hemispheres. That's a myth that doesn't work at bathroom sink scales. It's because large-scale weather systems spanning hundreds of miles are deflected by the Coriolis effect. Air flowing toward a low-pressure center gets deflected to the right in the northern hemisphere and to the left in the southern hemisphere, creating the characteristic spiral. Without Earth's rotation, we wouldn't have hurricanes as we know them. We might have storms, but they wouldn't have the organized rotating structure that makes hurricanes so powerful and so dangerous. Venus provides an interesting contrast to Earth. Venus rotates very slowly and in the opposite direction to most planets. We call this retrograde rotation. While Earth rotates west to east, taking 24 hours, Venus rotates east to west, taking 243 Earth days. A day on Venus is longer than a year on Venus. Venus orbits the Sun in 225 Earth days. Why does Venus rotate backwards? The most likely explanation is a massive collision early in Venus's history. A large object, perhaps the size of Mars, struck Venus with enough force to flip its rotation. Or perhaps multiple smaller collisions over time gradually reversed its spin. We don't know for certain. What we do know is that this retrograde rotation creates unusual dynamics in Venus's atmosphere. The atmosphere superrotates, meaning it circles the planet much faster than the surface rotates. While the surface takes 243 days to rotate once, The upper atmosphere circles the planet in just 4 days. That's about 60 times faster than the surface. The winds at high altitude are moving at over 200 miles per hour. This superrotation is still not fully understood. It's driven by complex interactions between solar heating, atmospheric circulation, and the planet's slow rotation. Venus shows us that rotation can take many forms and can drive atmospheric dynamics in unexpected ways. Uranus provides another example of unusual rotation. Uranus is tilted on its side. Its rotation axis lies almost in the plane of its orbit around the Sun. Most planets have rotation axes roughly perpendicular to their orbital planes, tilted by modest amounts, like Earth's 23.5 degrees. But Uranus is tilted by 98 degrees, meaning its poles alternately point almost directly at the Sun as it orbits. This creates extreme seasons. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness, as Uranus completes its 84-year orbit around the Sun. What caused this dramatic tilt? Most likely, one or more massive collisions during the formation of the solar system. A large object struck Uranus hard enough to knock it over onto its side. The moons of Uranus share this tilted orientation, suggesting the collision happened after the moons formed and the entire system was reoriented together. Despite this unusual orientation, Uranus still rotates fairly quickly, completing one rotation every 17 hours and 14 minutes. Faster than Earth. And like Earth, Uranus has a magnetic field generated by rotation and convection in its interior. But because of the extreme tilt, Uranus's magnetic field is oriented at a strange angle relative to its rotation axis, creating complex interactions with the solar wind. These examples show that while rotation is universal, the details vary enormously depending on the history and circumstances of each object. Let's think about rotation in the context of planetary rings. Saturn is famous for its spectacular rings, but all the gas giant planets have rings to some extent. These rings are made of countless small particles, ranging from dust grains to house-sized boulders, all orbiting the planet. The rings exist because of rotation and tidal forces. If a moon or other object comes too close to a planet, tidal forces can overcome the object's own gravity and tear it apart. The distance at which this happens is called the Roche limit. Inside the Roche limit, objects can't hold themselves together. They get pulled apart by tidal forces. Saturn's rings exist inside Saturn's Roche limit. They might be the remains of a moon that wandered too close and was torn apart. Or they might be material that was never able to coalesce into a moon in the first place because tidal forces prevented it. Either way, the particles in the rings are in orbit around Saturn, each one following its own path, determined by gravity and angular momentum. The ring particles closer to Saturn orbit faster than those farther out, following Kepler's laws. This differential rotation, different parts moving at different speeds, is what keeps the rings flat and stable. Collisions between particles average out any vertical motion, while the rotation prevents everything from falling into the planet. The structure within Saturn's rings, the gaps and divisions, is created by gravitational interactions with Saturn's moons. A moon orbiting outside the rings can create resonances, where ring particles at certain distances orbit in whole number ratios with the moon's orbit. These resonances sweep gaps in the rings. The Cassini division, the largest gap in Saturn's rings, is created by a 2-to-1 resonance with the moon Mimas. Ring particles in the Cassini division would orbit Saturn twice for every one orbit of Mimas, and this resonance destabilizes their orbits, clearing out the gap. So the detailed structure of planetary rings is a consequence of rotation and gravitational interactions playing out over millions of years. Let's shift to thinking about rotation in the early universe. We've talked about how galaxies and stars inherited rotation from the clouds they formed from. But where did those clouds get their rotation? In the very early universe, shortly after the Big Bang, matter was distributed almost uniformly. The density was almost the same everywhere, but not exactly. There were tiny variations, quantum fluctuations, that had been amplified by cosmic inflation in the first fraction of a second after the Big Bang. These density fluctuations were incredibly small, differences of about 1 part in 100,000, but they were crucial. Slightly denser regions had slightly stronger gravity. Over time, they attracted matter from their surroundings and grew denser. As matter flowed toward these overdense regions, it didn't fall straight in. Remember, different parts of the early universe had slightly different velocities. These velocity differences created angular momentum. As matter spiraled inward toward the growing density fluctuations, that angular momentum caused the collapsing regions to rotate. Over hundreds of millions of years, these rotating, collapsing regions formed the first galaxies. So the rotation of galaxies can be traced back to velocity differences in the early universe, which in turn came from quantum fluctuations in the first moments after the Big Bang. Rotation is literally built into the universe at the quantum level. This raises profound questions about the nature of the Big Bang itself. Did the Big Bang have angular momentum? Was the entire universe rotating from the very beginning? Or did rotation emerge from quantum fluctuations as the universe expanded? These are questions at the frontier of cosmology. Current observations suggest the universe as a whole is not rotating, or if it is, the rotation is so slow we can't detect it. But we can only observe the part of the universe within our cosmic horizon, the region from which light has had time to reach us since the Big Bang. The entire universe could be vastly larger than what we can see. If it is rotating, but the rotation period is much longer than the age of the universe, we wouldn't be able to detect it from our limited perspective. Some cosmologists have proposed that the universe could be rotating with a period of trillions of years, far too slow for us to measure. Others argue that any rotation would be averaged out by cosmic inflation, leaving us with an effectively non-rotating universe on the largest scales. This is an open question. Let's think about rotation and time. Einstein's theory of relativity tells us that space and time are not separate, but are woven together into spacetime. Rotation affects both space and time. We've mentioned frame dragging, where a rotating object drags spacetime around with it. But there's another effect called gravitational time dilation that's affected by rotation. Clocks at different distances from a rotating mass run at different rates. A clock on the surface of a rotating planet runs slightly slower than a clock in orbit above it, not just because of the difference in gravitational potential, but also because of the rotation. For Earth, the effect is tiny. A clock at the equator, where rotational velocity is highest, runs slower than a clock at the poles by about 30 nanoseconds per day. This is measurable with atomic clocks, but irrelevant for everyday life. But for rapidly rotating objects like neutron stars, the effect becomes significant. Time literally runs at different rates, at different locations on a spinning neutron star. At the equator, where the surface is moving at a substantial fraction of the speed of light, time runs noticeably slower than at the poles. If you could somehow stand on the equator of a rapidly spinning neutron star, you would age more slowly than someone standing at the pole. This isn't just a theoretical curiosity. It affects how we interpret observations of neutron stars and how we model their structure and behavior. Rotation also affects the shape of objects. A non-rotating sphere is the most stable shape under gravity alone. But when you add rotation, centrifugal effects cause the object to bulge at the equator and flatten at the poles. Earth is not a perfect sphere. It's an oblate spheroid, slightly flattened at the poles and bulging at the equator. The difference between the equatorial radius and the polar radius is about 13 miles. This bulge is caused by Earth's rotation. The faster an object rotates, the more pronounced the bulge. Jupiter rotates very quickly, once every 10 hours, and it's visibly flattened. You can see the oblateness in telescope images. Jupiter's equatorial diameter is about 7% larger than its polar diameter. Rapidly rotating stars are even more dramatically flattened. Some stars rotate so fast they're nearly twice as wide at the equator as they are from pole to pole. These stars are shaped like pancakes rather than spheres. The star Achernar, one of the brightest stars in the sky, visible from the southern hemisphere, is one of the flattest stars known. It rotates so rapidly that its equatorial radius is about 50% larger than its polar radius. This extreme flattening affects the star's brightness and temperature. The poles are hotter and brighter than the equator because the flattened shape means the poles have less mass above them pressing down, so they're compressed less and have lower density. Lower density means less opacity, so radiation from the hot interior can escape more easily, making the poles brighter. This effect is called gravity darkening. The equator of a rapidly rotating star appears dimmer than the poles, not because it's cooler, but because the light has a harder time escaping through the thicker equatorial regions. Rotation affects stellar evolution in other ways too. Rotating stars mix their fuel more efficiently than non-rotating stars. Convection and rotational mixing bring fresh hydrogen from the outer layers down into the core where fusion occurs, extending the star's lifetime. Rotating stars also lose mass more easily. The centrifugal effect at the equator partially counters gravity, making it easier for stellar winds to carry material away. Massive stars, rotating near their breakup speed, can shed significant mass over their lifetimes, affecting how they evolve and what kind of remnant they leave behind when they die. Some massive stars rotate so fast they lose enough mass that they don't explode as supernovae at all. Instead, they collapse directly into black holes, barely making a whimper in the cosmic sense. The rotation rate of a star when it forms depends on the angular momentum of the cloud it formed from, and on how much of that angular momentum gets carried away by magnetic fields and outflows during the formation process. Young stars often rotate quickly and then slow down over millions of years as magnetic braking transfers angular momentum from the star to its stellar wind. By the time a star like the Sun reaches middle age, billions of years old, its rotation has slowed considerably. The Sun rotates much slower now than it did when it first formed. In another billion years, it will rotate even more slowly. This gradual spin-down is a normal part of stellar aging for stars with outer convective zones that can generate magnetic fields. Let's think about rotation in the context of orbital mechanics and how we use rotation for space travel. When we send spacecraft to other planets, we take advantage of Earth's rotation to help launch them. Most launch sites are located as close to the equator as practical because that's where Earth's rotational velocity is highest. Launching eastward from the equator, you get a free boost of about 1,040 miles per hour from Earth's rotation. That's velocity you don't have to add with rockets, saving fuel and allowing for heavier payloads. The European Space Agency launches from French Guiana, very close to the equator. NASA launches from Florida, not as close, but closer than sites at higher latitudes. Russia launches from Kazakhstan, farther north, which is less efficient, but was chosen for historical and strategic reasons. Once a spacecraft is in orbit, rotation becomes crucial for stability and control. Most satellites and spacecraft spin, either rotating around an axis for stabilization or using gyroscopes to control orientation. Spinning stabilizes a spacecraft, the same way spinning stabilizes a bicycle wheel or a gyroscope. The angular momentum resists changes in orientation. Communications satellites in geostationary orbit are rotating at exactly the same rate. Earth rotates, so they appear to hover over one spot on the equator. This is incredibly useful for communications because ground stations can point at a fixed location in the sky rather than tracking a moving satellite. To achieve a geostationary orbit, a satellite must be at an altitude of 22,236 miles above the equator and moving at about 7,000 miles per hour. At that specific altitude and speed, the orbital period matches Earth's rotation period exactly. This is an example of how rotation on one scale, Earth's rotation, dictates the properties of rotation on another scale, satellite orbits. Spacecraft traveling to other planets use gravitational assists or gravity slingshots to change their velocity and trajectory. As a spacecraft passes close to a planet, it's deflected by the planet's gravity. From the spacecraft's perspective, it's following a curved path around the planet. But, from the Sun's perspective, the spacecraft can gain or lose velocity depending on whether it approaches the planet from behind or in front in the planet's orbit. This is a transfer of angular momentum and energy from the planet's orbit to the spacecraft's trajectory. The planet's rotation around the Sun slows down infinitesimally, and the spacecraft speeds up significantly. Or vice versa. The Voyager spacecraft used multiple gravitational assists from Jupiter, Saturn, Uranus, and Neptune to achieve the velocities needed to escape the solar system. Each encounter was carefully timed to maximize the transfer of angular momentum. Without these assists, we wouldn't have had enough rocket fuel to send Voyager to the outer solar system and beyond. The rotation and orbital motion of the planets made it possible. Let's consider rotation in the context of accretion disks around black holes and neutron stars. We mentioned earlier that material falling toward a compact object forms a rotating disk. These accretion disks are among the most energetic phenomena in the universe. The inner parts of the disk are moving at a significant fraction of the speed of light, orbiting just outside the event horizon of a black hole or just above the surface of a neutron star. As material spirals inward, friction between adjacent parts of the disk heats the material to millions of degrees. This superheated gas emits X-rays and gamma rays, making accreting black holes and neutron stars some of the brightest objects in the X-ray sky. The rotation of the disk is critical to this process. Without rotation, material would fall straight into the black hole or neutron star and wouldn't release nearly as much energy. It's the rotational motion that allows the material to orbit for a while, colliding with other material and heating up through friction before finally falling in. The luminosity of an accreting black hole depends on how much material is falling in and how efficiently that material converts its gravitational potential energy into radiation. The efficiency can be as high as 10 to 40%, meaning 10 to 40% of the infalling mass gets converted to energy according to E equals mc squared. For comparison, nuclear fusion in the core of a star converts about 0.7% of mass to energy. Accretion onto a rotating black hole is 10 to 50 times more efficient than nuclear fusion. This makes accreting black holes incredibly luminous. A supermassive black hole, actively accreting at the center of a galaxy, can outshine the entire rest of the galaxy, which contains hundreds of billions of stars. We call these active galactic nuclei, or quasars. They're powered by rotation. Material spiraling into the black hole, releasing tremendous energy as it does so. The jets that some black holes launch are also powered by rotation. The exact mechanism is still debated, but it involves magnetic fields threading the accretion disk and the rotation of the black hole itself, extracting energy from the rotating spacetime. These jets can extend for millions of light years, carrying energy and momentum far beyond the galaxy that hosts the black hole. The jets affect the intergalactic medium, heating gas, preventing it from cooling and forming new stars, and shaping the evolution of galaxy clusters. Rotation at the scale of a black hole a few miles across affects the evolution of structures millions of light years in size. Let's think about rotation in the context of star formation in more detail. We've discussed how collapsing clouds form rotating disks. But within those disks, rotation affects how stars actually ignite and begin fusing hydrogen. As a protostar contracts, rotation causes it to flatten. If it's rotating too fast, centrifugal forces prevent it from contracting enough to reach the temperature and density needed for fusion. The protostar has to shed angular momentum to continue contracting. This happens through several mechanisms. Magnetic fields threading through the protostar and the surrounding disk can transfer angular momentum outward, allowing the central protostar to contract. Outflows and jets, launched from the protostar's poles, carry away mass and angular momentum. If you look at regions of active star formation with telescopes, you see these bipolar outflows, jets of gas shooting out from young stars, perpendicular to their accretion disks. These jets are one of the primary ways young stars shed the excess angular momentum that would otherwise prevent them from becoming stars. Without this mechanism, star formation would be much less efficient. Many collapsing clouds would spin themselves apart rather than forming stars. The fact that we see so many stars tells us that angular momentum removal is effective. Rotation also affects whether a collapsing cloud fragments into multiple stars. A slowly rotating cloud might collapse into a single star. A rapidly rotating cloud might fragment into a binary or multiple star system. Most stars are actually in binary or multiple systems. Single stars, like the Sun, are common, but not the majority. This suggests that rotation and fragmentation during collapse are important processes. Binary stars form when a rotating cloud breaks into two or more clumps, each of which continues collapsing while orbiting the others. The resulting system is two or more stars orbiting their common center of mass. These binary systems preserve the rotation of the original cloud in the form of orbital motion. Close binary stars, where the two stars are just a few million miles apart, can interact in dramatic ways. If one star expands into a red giant, its outer layers can overflow onto the companion, transferring mass and angular momentum. This can spin up the companion star, rejuvenate it, and change the evolution of both stars in complex ways. Some exotic objects, like blue stragglers, are thought to form from mass transfer in binary systems. A blue straggler is a star that appears younger and more massive than it should be, given the age of the star cluster it's in. The explanation is that it gained mass from a companion in a binary system, effectively growing larger and resetting its evolution. Rotation and binary interactions create a huge variety of stellar outcomes that wouldn't exist if stars formed and evolved in isolation. Now, let's think about rotation from a philosophical perspective. Why should rotation be so fundamental? Why should angular momentum be conserved? The answer lies in symmetry. As we've mentioned, conservation laws arise from symmetries. But what does that really mean? The mathematician Noether proved in 1915 that every symmetry of the laws of physics corresponds to a conservation law. If the laws don't change when you shift forward in time, energy is conserved. If the laws don't change when you shift to a different location in space, momentum is conserved. If the laws don't change when you rotate your perspective, angular momentum is conserved. These are not separate facts. They're all consequences of a deep connection between symmetry and conservation discovered by Noether's theorem. Rotational symmetry means the laws of physics are the same, regardless of which direction you call north or up or forward. There's no preferred direction in space. Physics works the same way, whether your lab is facing east or west. This symmetry, this fundamental sameness of physics in all directions, is what gives rise to conservation of angular momentum. And because angular momentum is conserved, rotation never disappears. It can be transferred, redistributed, shared between objects, but the total angular momentum of a closed system remains constant. This is why rotation is universal. It's not an accident or a coincidence. It's a mathematical necessity arising from the structure of physical law. The universe has rotational symmetry, therefore angular momentum is conserved, therefore rotation persists everywhere we look. You could imagine a different universe with different symmetries, leading to different conservation laws. Maybe a universe where space has a preferred direction, breaking rotational symmetry. In such a universe, angular momentum wouldn't be conserved, and rotation might not be stable. Objects might spontaneously start or stop spinning. The universe would be very strange, very different from ours. It's unclear whether complex structures like galaxies and stars could even form in such a universe. So, rotation isn't just a feature of our universe. It might be a requirement for any universe capable of developing complex structure and ultimately life. Let's consider rotation in quantum mechanics more carefully. We mentioned that particles have intrinsic spin, a quantum mechanical property that's not actual rotation but has many similar features. The spin of a particle is quantized. An electron always has spin 1/2, never more, never less. You can measure the spin along any axis you choose, and you'll always get one of two values, spin up or spin down along that axis. The choice of axis is arbitrary, a consequence of rotational symmetry. But once you choose an axis and measure the spin along it, the particle is in a definite state relative to that axis. If you then measure the spin along a different axis, you disturb that state and get a probabilistic result. This is one of the strange features of quantum mechanics that has no classical analog. The spin of particles affects how they interact. Electrons with opposite spins can occupy the same orbital in an atom. Electrons with parallel spins cannot, because of the Pauli exclusion principle. This is why the periodic table has the structure it does, with elements having different chemical properties based on how many electrons they have and how those electrons are arranged in shells. Without spin, chemistry would be completely different. Atoms wouldn't have the shell structure they do. Chemical bonding would work differently. The molecules necessary for life might not be stable. Spin also affects particle interactions at a more fundamental level. The strong nuclear force, which holds atomic nuclei together, depends on the spin states of quarks inside protons and neutrons. The electromagnetic force depends on the spin of photons. The weak nuclear force that governs radioactive decay involves particles with different spins. So spin, the quantum mechanical analog of rotation, is woven into the fabric of particle physics. It's not an add-on or a secondary property. It's fundamental to how particles exist and interact. And remarkably, this quantum mechanical spin is connected to classical rotation through angular momentum. When you add up the spins of all the particles in a macroscopic object, you can get classical angular momentum. A rotating object's angular momentum is the sum of the orbital angular momenta of its atoms and the intrinsic spins of all its particles. Mostly, the orbital part dominates for large objects, but the spin contribution is there, linking the quantum world to the classical world. Let's explore some practical applications of understanding rotation. Navigation has relied on rotation for centuries. Before GPS, ships navigated by the stars, using the apparent rotation of the celestial sphere to determine latitude and longitude. The altitude of Polaris, the North Star, tells you your latitude directly in the northern hemisphere. Polaris appears fixed while other stars rotate around it because it's very close to the projection of Earth's rotation axis on the sky. The stars appear to rotate because Earth is rotating. By measuring how stars move across the sky and knowing the time, navigators could determine their position. This required accurate clocks and careful observations. The invention of the marine chronometer in the 18th century, a clock accurate enough to keep time at sea, revolutionized navigation. It allowed sailors to determine longitude by comparing local time, determined from the sun's position, with the time at a reference meridian like Greenwich. The difference in time tells you how far east or west you are. This is fundamentally using Earth's rotation as a clock and a reference frame. Modern navigation uses gyroscopes, devices that maintain their orientation because of conservation of angular momentum. A spinning gyroscope resists changes to its orientation. If you mount a gyroscope in a vehicle, you can detect when the vehicle turns by measuring how the gyroscope's orientation changes relative to the vehicle. This is how inertial navigation systems work. They use accelerometers to measure linear motion and gyroscopes to measure rotation. By integrating these measurements over time, they can track the vehicle's position without any external references. This is crucial for submarines underwater, where GPS doesn't work, and for spacecraft beyond Earth, where GPS doesn't exist. Gyroscopes in smartphones detect when you rotate your phone, allowing the screen to rotate and enabling motion-controlled games. Gyroscopes in drones and aircraft help stabilize them and maintain orientation. All of these applications depend on understanding and exploiting rotation. Let's think about rotation in the context of climate and weather. Earth's rotation affects climate in profound ways. The Coriolis effect deflects ocean currents and wind patterns, creating the major circulation cells of the atmosphere. Warm air rises at the equator, flows toward the poles at high altitude, sinks at mid-latitudes, and returns toward the equator at low altitude. But the Coriolis effect deflects these flows, creating the trade winds, westerlies, and polar easterlies. These wind patterns drive ocean currents, like the Gulf Stream and the Kuroshio Current, which transport enormous amounts of heat from the tropics toward the poles. The Gulf Stream alone carries about 1.4 petawatts of thermal energy, about 100 times the worldwide energy consumption of human civilization. This heat transport moderates climate, making Western Europe much warmer than it would be at its latitude without the Gulf Stream. The rotation of Earth also affects the length of day and the seasons through its axial tilt. We've mentioned this, but it's worth emphasizing how crucial it is. Without the 23.5-degree axial tilt, Earth wouldn't have seasons. The tropics would receive constant, intense sunlight year-round, while the poles would be perpetually cold. The temperate zones, where most of human civilization developed, would be narrower and less hospitable. The tilt itself is a consequence of rotational dynamics during Earth's formation, specifically the collisions that built Earth and possibly the giant impact that formed the Moon. Different collisions would have given a different tilt, resulting in different seasons and potentially a very different climate. Mars has a similar tilt to Earth, about 25 degrees, and experiences seasons for the same reason. But Mars has much less atmospheric mass and no large moon to stabilize its tilt. Over hundreds of thousands of years, Mars's tilt varies chaotically between about 20 and 60 degrees. When the tilt is high, the poles receive more sunlight, and the polar ice caps sublimate, releasing carbon dioxide into the atmosphere and temporarily thickening it. When the tilt is low, the poles are colder, and carbon dioxide freezes out, thinning the atmosphere. These variations in Mars's rotation and tilt drive long-term climate cycles that have shaped the planet's surface. Earth's tilt is stabilized by the Moon. The Moon's gravity exerts a torque on Earth's equatorial bulge, preventing the tilt from varying as wildly as Mars's does. Without the Moon, Earth's tilt could vary by tens of degrees over hundreds of thousands of years, causing dramatic climate shifts that might have prevented complex life from evolving. So, the Moon's presence, which itself is a consequence of a collision involving rotation and angular momentum, has stabilized Earth's rotation and made our climate more predictable and conducive to life. Another interesting effect of rotation is the Foucault pendulum, a simple device that demonstrates Earth's rotation. A pendulum, a weight hanging from a long wire, naturally swings back and forth in a fixed plane. But if you let it swing for hours, you'll notice the plane of the swing slowly rotates. This isn't because anything is pushing the pendulum. It's because Earth is rotating beneath it. The pendulum maintains its orientation in space, while Earth turns under it, making it appear that the pendulum is rotating. At the North or South Pole, the pendulum's swing plane would complete one full rotation in 24 hours. At the equator, there would be no apparent rotation. At intermediate latitudes, the rotation rate depends on latitude. Léon Foucault first demonstrated this in 1851 with a pendulum in the Panthéon in Paris, providing clear visual proof that Earth rotates. It's a beautiful example of how rotation on one scale, Earth's daily spin, manifests in the behavior of objects on a human scale, a swinging pendulum. We can use this principle to build devices that detect rotation for navigation and scientific purposes. Think about the role of rotation in shaping planetary interiors. Earth's core is divided into a solid inner core and a liquid outer core. The outer core is iron and nickel in molten form, flowing and convecting because of heat escaping from the center. The combination of this convection and Earth's rotation creates electric currents in the conducting liquid metal. These currents generate Earth's magnetic field through the dynamo effect. The magnetic field protects Earth's atmosphere from being stripped away by the solar wind. Mars lost most of its atmosphere billions of years ago, partly because its magnetic field shut down when its core cooled and stopped generating a dynamo. Without rotation, there would be no dynamo. Without a dynamo, there would be no magnetic field. Without a magnetic field, planets are vulnerable to losing their atmospheres and becoming inhospitable. So, rotation is indirectly necessary for maintaining habitable conditions on planets. The rate of rotation affects the strength of the magnetic field. Jupiter rotates very quickly, once every 10 hours, and has an extremely strong magnetic field, about 20,000 times stronger than Earth's. Venus rotates very slowly and has almost no magnetic field. This is a direct consequence of rotation rate affecting the dynamo process. Let's zoom out one more time and think about rotation in the most extreme environments we know of. Near the event horizon of a black hole, space-time is so warped that our intuitions completely break down. For a rotating black hole, the structure is even more complex than for a non-rotating one. There's an inner horizon and an outer horizon, defining regions where different physical processes dominate. There's the ergosphere, where frame dragging is so extreme that nothing can stay still. And there's the ring singularity, where all the mass of the black hole is concentrated not at a point, but in a ring shape. Rotating black holes are described by the Kerr metric, and they have fascinating properties. For one, it's theoretically possible to orbit very close to the event horizon in stable orbits if you're moving in the same direction as the black hole's rotation. The frame dragging actually helps stabilize these orbits. If you tried to orbit against the rotation, the orbit would be unstable, and you'd either fall in or be flung out. For extreme rotating black holes, called maximally rotating or extremal black holes, the event horizon and the inner horizon merge. The black hole is spinning as fast as physics allows. If it tried to spin faster, the mathematics breaks down and the solution becomes unphysical. There's a cosmic speed limit on rotation, just as there's a cosmic speed limit on velocity. Nothing can move faster than light, and no black hole can rotate faster than the extremal limit. Real astrophysical black holes probably don't reach this extreme limit because accretion tends to slow them down before they can spin up to maximum, but some come close. The black hole at the center of quasar, GRS, 1915 plus 105, is estimated to be spinning at over 98% of the maximum rate. It's rotating so fast that the inner edge of its accretion disk is being dragged around at a substantial fraction of the speed of light. These extreme rotations release enormous amounts of energy, powering some of the brightest objects in the universe. As a final thought, consider the philosophical implications. The universe is not static. it's not still. Everywhere you look, things are moving, spinning, orbiting. This motion is fundamental to the existence of structure. Without rotation, clouds would collapse directly into points. Planets couldn't form. Galaxies would be unstable. The universe would be a very different, much simpler, probably lifeless place. The fact that we exist to ask these questions is in part because the universe spins. Rotation enables complexity. It allows matter to organize into planets, stars, galaxies, and ultimately life. Every breath you take is possible because Earth is spinning, creating day and night, seasons, weather patterns, and a magnetic field. Every element in your body, heavier than hydrogen and helium, was forged in spinning stars that lived, died, and scattered their remains into space. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it was made in stars and distributed by processes intimately connected to rotation. When you look up at the night sky and see stars, you're seeing light from objects that are all rotating, all orbiting, all part of a cosmos in perpetual motion. And you're standing on a rotating planet, orbiting a rotating star in a rotating galaxy. You're part of the cosmic spin. Your existence is proof that rotation isn't just a feature of the universe. It's essential to everything that makes the universe interesting, complex, and alive. But let's dig deeper into some specific phenomena that reveal just how pervasive and important rotation really is. Consider the formation of protoplanetary disks in more detail. When we observe star-forming regions with telescopes like the Atacama Large Millimeter Array, ALMA, we see exquisite details of these rotating disks around young stars. The disks aren't smooth. They show gaps, rings, spiral patterns, and asymmetries. These features are created by young planets forming within the disk, their gravity carving out gaps and creating spiral density waves. The discovery of these structures has revolutionized our understanding of how planetary systems form. We can now watch planets being born in real time. Well, real time in the astronomical sense, which means watching the same system over years and decades to see changes. The rotation of these disks determines where planets can form. Close to the star, where temperatures are high, only rocky planets can form because ices and volatile compounds evaporate. Farther out, beyond the frost line where water ice can exist, gas giant planets can form. They accumulate massive atmospheres of hydrogen and helium from the surrounding disk. The locations of these zones depend on the star's temperature and the disk's rotation, which determines how material is distributed. Jupiter formed beyond the frost line in our solar system and became massive enough to prevent another planet from forming in the asteroid belt between Mars and Jupiter. Jupiter's gravity stirred up the asteroid belt, preventing the rocky bodies there from coalescing into a planet. This is why we have an asteroid belt rather than a fifth rocky planet. Jupiter's formation and the rotation of the solar nebula shape the architecture of our solar system. In other planetary systems observed around other stars, we see a huge variety of configurations. Some have hot Jupiters, gas giant planets orbiting extremely close to their stars, closer than Mercury orbits our Sun. These planets couldn't have formed where we find them today because it's too hot. They must have formed farther out and then migrated inward. Migration happens through interactions with the protoplanetary disk. The planet's gravity creates spiral waves in the disk, and these waves exert torques on the planet that can cause it to spiral inward toward the star or outward away from the star. depending on the exact configuration. This migration is driven by the exchange of angular momentum between the planet and the disk. The rotating disk literally pushes planets around, determining the final architecture of the planetary system. So, when we observe exoplanets and find them in surprising configurations, we're seeing the consequences of complex rotational dynamics playing out over millions of years during planetary system formation. Let's explore tidal locking in more depth because it's a striking example of how rotation evolves over time. Tidal locking occurs when an object's rotation period matches its orbital period, so it always shows the same face to the object it's orbiting. Our Moon is tidally locked to Earth. One side, the near side, always faces us. The other side, often incorrectly called the dark side, though it receives just as much sunlight, never faces Earth. This happened because Earth's gravity created tides in the Moon's rock. Even though rock seems completely solid, over millions of years, the gravitational stress caused by tides creates friction and heat. This friction dissipates rotational energy, slowing the Moon's spin until it matched its orbital period. Now the Moon is in the lowest energy configuration possible for its rotation given its orbital parameters. The same process is happening to Earth, but much more slowly because Earth is more massive and the tidal forces from the Moon are weaker relative to Earth's size. Eventually, billions of years from now, Earth will become tidally locked to the Moon as well. At that point, the same side of Earth will always face the Moon. If you were on that side, you'd see the Moon hanging motionless in the sky, never rising or setting. On the other side of Earth, you'd never see the Moon at all. This final configuration represents the lowest energy state for the Earth-Moon system's rotation. Tidal locking is extremely common in the universe. Most moons in the solar system are tidally locked to their planets. Many exoplanets orbiting close to their stars are probably tidally locked. A tidally locked planet has permanent day and night sides. One side eternally baking under the star's light, the other in perpetual darkness. This creates extreme temperature differences and potentially strange weather patterns as heat tries to flow from the day side to the night side. Some tidally locked exoplanets might be habitable in the twilight zone, the ring between day and night, where temperatures are moderate. But the habitability depends critically on atmospheric circulation, which is itself driven by the temperature differences caused by the tidal locking. So, rotation, or in this case, the lack of rotation relative to the orbit, shapes the potential habitability of worlds. Let's think about retrograde rotation again, but in more detail. Venus rotates backwards, but it's not alone. Uranus also has retrograde rotation, or at least it's tilted so far on its side that it's effectively rotating retrograde relative to its orbital plane. Several moons in the solar system have retrograde orbits, meaning they orbit their planets in the opposite direction from the planet's rotation. These retrograde orbits are thought to be captured objects, asteroids, or comets that were gravitationally captured by the planet rather than forming in the same protoplanetary disk. Triton, Neptune's largest moon, is in a retrograde orbit. It's probably a captured Kuiper belt object, similar to Pluto, that Neptune captured billions of years ago. The capture process would have involved a complex dance of gravitational interactions, possibly involving other moons or objects that were ejected or destroyed in the process. Triton's retrograde orbit means it's slowly spiraling inward toward Neptune. Tidal forces are causing its orbit to decay. In a few billion years, Triton will cross Neptune's Roche limit and be torn apart by tidal forces. The debris will form a spectacular ring system around Neptune, probably more impressive than Saturn's current rings. So retrograde rotation and retrograde orbits tell us about violent events in the past, collisions and captures that altered the natural rotation inherited from formation. They're exceptions that prove the rule. Normal rotation comes from the angular momentum of the forming system, and deviations from normal rotation require special explanations. Now, let's consider the role of rotation in generating magnetic fields in more detail, because this is crucial for habitability. Earth's magnetic field extends far into space, creating a protective bubble called the magnetosphere. The magnetosphere deflects the solar wind, a constant stream of charged particles from the Sun that would otherwise strip away our atmosphere. Mars lost most of its atmosphere over billions of years, partly because its magnetic field failed. Mars's core cooled down, convection stopped, the dynamo shut off, and the magnetic field disappeared. Once that happened, the solar wind began directly hitting the Martian atmosphere, gradually stripping it away. Mars's atmosphere today is less than 1% as thick as Earth's. Early Mars probably had a much thicker atmosphere and liquid water on its surface. The loss of the magnetic field, caused by the cessation of internal rotation and convection, was one of the key factors in Mars becoming the cold, dry desert world we see today. Earth has maintained its magnetic field because our planet is large enough that the core is still hot and convection continues. The rotation of Earth, combined with convection in the outer core, creates the dynamo that generates the magnetic field. As long as Earth keeps rotating and the core stays hot, the magnetic field will persist. This is expected to continue for billions of years. The strength and orientation of Earth's magnetic field changes over time. The magnetic poles wander, and occasionally the field completely reverses, with north and south poles swapping positions. These reversals happen irregularly, roughly every few 100,000 years on average, though the time between reversals varies greatly. The last reversal was about 770,000 years ago. We're overdue for another one by historical standards, but that doesn't mean it's imminent. It could happen tomorrow, or 100,000 years from now. During a reversal, the field doesn't disappear completely, but it becomes more complex and weaker. The magnetosphere is less effective at shielding Earth from the solar wind during these transition periods. This might have consequences for life, possibly increasing radiation exposure and affecting climate through increased cosmic ray bombardment of the atmosphere. Some scientists have speculated that magnetic reversals might correlate with mass extinctions, though the evidence is inconclusive. The fact that magnetic reversals are recorded in rocks as iron minerals align with the magnetic field when the rock forms has been crucial for understanding plate tectonics. The pattern of magnetic stripes on the ocean floor, alternating between normal and reversed polarity, provided key evidence that new ocean crust is continuously being created at mid-ocean ridges and spreading outward. This was one of the major discoveries that led to the acceptance of plate tectonics in the 1960s. So, Earth's rotation generates a magnetic field that protects our atmosphere. And the record of that magnetic field's changes has helped us understand the dynamic nature of our planet's surface. Let's explore the relationship between rotation and gravitational waves. When two massive objects, like black holes or neutron stars, orbit each other, they're accelerating. Any accelerating mass produces gravitational waves, ripples in spacetime itself. For slowly moving objects, these waves are incredibly weak and undetectable. But for very massive objects moving at high speeds very close together, the gravitational waves become strong enough to detect. As two black holes spiral toward each other, they're losing energy to gravitational wave radiation. This loss of energy causes them to spiral inward faster, which makes them emit stronger gravitational waves, which causes them to spiral inward even faster, in a runaway process called an inspiral. The orbital period gets shorter and shorter. At first, they might be orbiting each other once every few hours. As they get closer, the period drops to minutes, then seconds, then milliseconds. In the final fraction of a second before merger, they're orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light. The gravitational waves they emit during this final inspiral and merger are what LIGO and other gravitational wave detectors observe. The signal is called a chirp because when you convert it to sound, it sounds like a bird's chirp rising in pitch. The increasing frequency of the gravitational waves corresponds to the increasing orbital frequency as the black holes spiral together. The detection of gravitational waves has opened a completely new way of observing the universe. Instead of looking at light, we're now listening to the vibrations of space-time itself, caused by the most violent events in the universe, collisions of black holes and neutron stars. Each detection tells us about the masses and spins of the objects involved. The spin of a black hole affects the gravitational wave signal in subtle ways that can be measured. Highly spinning black holes produce different waveforms than slowly spinning ones. By analyzing the gravitational wave signal, we can determine not just the masses of the merging objects, but also their spins. This has revealed that some black holes are spinning rapidly, others more slowly, giving us clues about how they formed and what their histories were. Some black hole mergers involve black holes with aligned spins, both spinning in the same direction as their orbit. Others involve misaligned spins, sometimes even tilted perpendicular to the orbital plane. These spin configurations tell us about the formation history of the binary system. Aligned spins suggest the black holes formed together from a binary star system. Misaligned spins suggest the black holes came together through dynamical interactions in a dense stellar environment, like a globular cluster. So the rotation, the spin of these black holes, encoded in the gravitational waves they emit, reveals their origins. Neutron star mergers detected through gravitational waves are even more interesting because they also produce electromagnetic signals. When two neutron stars merge, they don't just emit gravitational waves. They also produce a bright explosion called a kilonova, visible in optical, infrared, and other wavelengths. In August 2017, LIGO and Virgo detected gravitational waves from a neutron star merger. Within seconds, telescopes around the world were pointed at the source. They detected a kilonova, the first time a gravitational wave event was observed in both gravitational waves and light. This merger produced heavy elements like gold, platinum, and uranium through rapid neutron capture, a process called R-process nucleosynthesis. The material ejected from the merger, enriched with these heavy elements, will eventually be incorporated into new stars and planets. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all of it was created in neutron star mergers. These mergers are rotating systems, spinning neutron stars, spiraling together and colliding, and their rotation is crucial to the physics that creates heavy elements. The rapid rotation and magnetic fields in the merger, ejector, create the conditions needed for our process nucleosynthesis. Without rotation, the physics would be different, and we might not have heavy elements in the abundance we observe. So once again, rotation at the largest scales, merging neutron stars, affects the composition of matter at the smallest scales, individual atoms. Let's think about the rotation of galaxy superclusters and the cosmic web. The cosmic web is the largest scale structure in the universe, consisting of filaments of galaxies separated by vast voids. Recent studies have suggested that some of these filaments might be rotating. If you look at galaxies along a filament, they might show a slight tendency to be moving in one direction perpendicular to the filament's length, suggesting the entire filament is rotating around its long axis. This is controversial because measuring such rotation is incredibly difficult. The rotational velocities would be very slow, and the distances are so vast that small measurement errors can hide or mimic a rotation signal. But if it's real, it would mean rotation extends to the largest structures in the universe, hundreds of millions of light-years across. The origin of such rotation would be primordial, coming from the velocity differences in the early universe that grew into the cosmic web we see today. Some cosmological simulations show that filaments can acquire rotation as they form through the accretion of matter with net angular momentum. If this is correct, then rotation is not just a property of individual objects like stars and galaxies, but of the universe's entire large-scale structure. This would be a profound discovery, showing that angular momentum is distributed across the cosmos at every conceivable scale. Let's examine the rotation curves of galaxies in more detail because they're one of the key pieces of evidence for dark matter. A rotation curve plots orbital speed against distance from the galactic center. For the solar system, orbital speed decreases with distance. Mercury orbits faster than Earth, which orbits faster than Jupiter, which orbits faster than Neptune. This is what you'd expect based on Kepler's laws and the distribution of mass mostly concentrated in the Sun at the center. You'd expect the same pattern for galaxies. Most of the visible stars are concentrated in the central bulge, so you'd expect orbital speeds to drop off in the outer regions where there are fewer stars. But that's not what we observe. Rotation curves of spiral galaxies are flat or even slightly rising at large distances from the center. Stars in the outer parts of galaxies are moving just as fast as, or even faster than, stars closer to the center. This implies there's additional mass we can't see, distributed in a halo around the galaxy. This invisible mass is what we call dark matter. The flat rotation curves are some of the strongest evidence that dark matter exists. Without dark matter, galaxies would fly apart. The outer stars are moving so fast that the gravity from visible matter alone isn't enough to hold them in orbit. There must be additional gravitational pull from dark matter. Computer simulations of galaxy formation that include dark matter produce galaxies with rotation curves matching what we observe. Simulations without dark matter fail to produce realistic galaxies. The rotation, the spin of galaxies, directly reveals the presence of dark matter through its gravitational influence on the orbital speeds of stars and gas. This is one of the most important discoveries in modern astronomy, and it came from carefully measuring rotation. Now, let's think about the role of rotation in the formation of jets from black holes and neutron stars. Jets are collimated beams of particles and radiation that shoot out from the poles of accreting black holes and neutron stars. Some jets extend for millions of light years, far beyond the galaxy containing the black hole. The jets are powered by the rotation of the accretion disk and possibly the rotation of the black hole itself. The leading theory for jet formation involves magnetic fields threading through the accretion disk. As the disk rotates, it twists the magnetic field lines, which can become wound up like a spring. The magnetic energy builds up until the field lines snap and reconnect, launching particles along the rotation axis at nearly the speed of light. This process, called magnetic reconnection, converts rotational energy from the disk into kinetic energy of the jet particles. Another mechanism, called the Blandford-Znaiec process, can extract rotational energy directly from a spinning black hole. The black hole's rotation drags spacetime around with it through frame dragging, and this rotating spacetime can twist magnetic field lines, creating an electric field that accelerates particles. Essentially, the black hole acts like a giant generator, converting its rotational energy into electromagnetic energy and particle acceleration. This process can be incredibly efficient, extracting a significant fraction of the black hole's rotational energy and beaming it out in the jets. The jets affect the surrounding environment profoundly. They plow into the intergalactic medium, heating gas, creating shock waves, and preventing that gas from cooling and forming new stars. This feedback from jets is thought to regulate the growth of galaxies. Without jets suppressing star formation, massive galaxies would turn all their gas into stars much faster than we observe. The jets keep the gas hot and prevent it from collapsing to form stars. So the rotation of a black hole, an object just a few miles across, can affect the evolution of an entire galaxy spanning hundreds of thousands of light years. This is rotation influencing structure on scales billions of times larger. Let's think about precession, a type of rotation that many rotating objects exhibit. Precession is when the axis of rotation itself rotates, tracing out a cone over time. Earth's rotation axis precesses with a period of about 26,000 years. This is called axial precession, or precession of the equinoxes. It's caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge. Because Earth is slightly flattened and bulges at the equator, the Sun and Moon's gravity exerts a torque trying to pull the bulge into alignment with the orbital plane. This torque causes the rotation axis to precess slowly. As a result, the position of the north celestial pole, the point in the sky that the north axis points toward, changes over time. Right now, Polaris is the North Star because it's close to the north celestial pole. But 5,000 years ago, the star Thuban in the constellation Draco was the North Star. In another 12,000 years, the bright star Vega will be the North Star. And in 26,000 years, we'll come full circle and Polaris will be the North Star again. This precession affects the timing of the seasons slightly. The vernal equinox, the first day of spring in the northern hemisphere, slowly shifts earlier in Earth's orbit over thousands of years. This is why the astrological signs, which were defined over 2,000 years ago, are now about a month off from the actual positions of the constellations. Precession also affects long-term climate cycles on Earth. Combined with variations in the eccentricity of Earth's orbit and the tilt of the axis, precession drives Milankovitch cycles. Climate variations with periods of tens of thousands to hundreds of thousands of years. These cycles are thought to trigger ice ages and warm periods. During times when northern hemisphere summers coincide with Earth being farthest from the Sun in its elliptical orbit, summers are cooler and snow and ice don't fully melt, allowing glaciers to grow. Over tens of thousands of years, this can lead to an ice age. The last ice age peaked about 20,000 years ago and ended about 11,000 years ago, in part due to changes in Earth's orbital parameters and precession. So, precession, a subtle effect of rotation, has profound consequences for Earth's climate over long timescales. Precession happens for other rotating objects too. Spinning tops precess, their axes tracing out cones as they spin. Gyroscopes precess when a force is applied perpendicular to their spin axis. Neutron stars can precess if their magnetic axis is tilted relative to their rotation axis. Pulsars sometimes show slow changes in their pulse properties that might be due to precession of the neutron star. Black holes with misaligned spins relative to their accretion disks can cause the disk itself to precess, creating complex time-dependent behavior in the X-ray emission from the system. Precession is another manifestation of rotational dynamics, showing that rotation is not always simple or steady, but can involve complex motions as different forces and torques interact. Let's explore the rotation of comets in more detail. Comets are icy bodies from the outer solar system that develop spectacular tails when they approach the Sun and their ices sublimate. As a comet approaches the Sun, solar heating causes ice on the surface to sublimate, turning directly from solid to gas without passing through a liquid phase. This gas streams away from the comet, carrying dust particles with it, creating the visible tail. But the sublimation doesn't happen uniformly across the comet's surface. The side facing the Sun heats up more than the night side. Irregularities in the surface mean some regions sublimate more than others. This uneven outgassing creates jets of gas shooting out from specific locations on the comet's surface. These jets exert force on the comet, and if the jets are angled, they create a torque that changes the comet's rotation. This is called non-gravitational force, and it can significantly alter a comet's orbit and rotation over time. Some comets have been observed to speed up or slow down their rotation as they approach the Sun. Some have even been observed to break apart, possibly because rotational stresses combined with outgassing weakened their structure. Comet 73, P. Schwarzmann-Wachmann, 3 broke into multiple pieces during its 2006 apparition. The rotation and outgassing created stresses that exceeded the comet's structural strength, tearing it apart. The rotation of comets also affects the shape of their tails. As the nucleus rotates, the jets turn on and off, depending on whether the active regions are in sunlight or shadow. This creates spiral patterns in the tail as material is released in pulses synchronized with the comet's rotation period. By observing these patterns, astronomers can determine the rotation period and axis of the comet without ever resolving its surface. The Rosetta spacecraft, which orbited Comet 67P Churyumov-Gerasimenko, observed its rotation and outgassing in unprecedented detail. The comet rotates once every 12.4 hours, and the rotation is complex because the comet has an irregular dumbbell shape. As the rotation axis precesses and the comet orbits the Sun, different regions receive varying amounts of sunlight at different times. This creates seasonal effects on a comet, just like Earth has seasons, but driven by rotation and orbital position. Rosetta observed jets turning on and off, changes in the comet's appearance, and even detected that the rotation period was slowly changing due to the torques from outgassing. This shows that even small objects like comets have complex rotational dynamics influenced by multiple factors. Let's consider the rotation of space stations and spacecraft. In the absence of gravity, as in Earth orbit, you experience weightlessness. But weightlessness has negative health effects over long periods, including muscle atrophy, bone loss, and cardiovascular deconditioning. To counteract this, future space stations and spacecraft designed for long-duration missions might use rotation to create artificial gravity. If you build a cylindrical or ring-shaped space station and rotate it, the rotation creates centrifugal effects that simulate gravity. People on the inside surface of the rotating station would feel a force pushing them toward the outside, similar to how you feel pushed outward when a car goes around a sharp curve. This artificial gravity could mitigate many of the health problems associated with long-term weightlessness. The amount of artificial gravity depends on the rotation rate and the radius of the station. For a given gravitational field, say Earth, normal gravity, a larger station can rotate more slowly than a smaller station. This is important because rapid rotation can cause disorientation and motion sickness due to Coriolis effects. If you walk in a rotating environment, the Coriolis effect makes it feel like forces are pushing you sideways. If the rotation is too fast, this becomes very disorienting. Studies suggest that a rotation rate of about 4 revolutions per minute or slower is tolerable for most people. To achieve Earth normal gravity at this rotation rate, the station would need a radius of about 56 meters or larger. For Mars-level gravity, about 38% of Earth's, a smaller radius would suffice, maybe around 20 meters. Designs for rotating space stations have been proposed since the 1950s. The classic image is a giant wheel slowly spinning in space, people living on the inside rim experiencing artificial gravity. No such station has been built yet because the cost and engineering challenges are enormous. But for future missions to Mars or beyond, where astronauts will be in space for months or years, artificial gravity through rotation might become necessary. This is using rotation to solve a practical problem, creating a gravitational environment where none naturally exists. There's also the concept of a tether system, where 2 spacecraft are connected by a cable and the whole system rotates around its center of mass. The 2 spacecraft experience artificial gravity, pulling them toward each other along the tether. This is a simpler concept than building a large rotating station, but it has its own challenges, like stabilizing the rotation and preventing the tether from breaking. Some proposals suggest using this for trips to Mars, with the spacecraft and a spent rocket stage connected by a tether and rotating to provide artificial gravity during the months-long voyage. Rotation, as a solution to the problem of weightlessness in space, shows yet another way that understanding rotation has practical applications for humanity's future. Thanks for joining me on this journey through rotation across the cosmos. From the spin of Earth beneath your feet to the rotation of galaxies billions of light years away, it's all connected by the same fundamental principle. Angular momentum is conserved, and rotation is eternal. The universe spins because it must, because the laws of physics demand it, because symmetry and conservation are woven into the fabric of reality itself.